What is going on, everybody? It's Mr. Gus, and I'm in the physics classroom today. Today, we're kind of recapping magnetic flux and then talking about what that means in terms of the phenomenon of electromagnetic induction. So to recap, we said flux. I've got my demonstrator right here, my B field demonstrator, right? If these straws all indicate a magnetic field, we said that flux is the measure of how many B field lines, the amount of B field going into a loop of wire or through some wire, right? Like if I have it completely surrounding this, I would say that the B field is my flux is maximized, right? The amount of cross-sectional area in the B field through it is maximized. There are two ways I can change that. Number one, I can slide this loop halfway out of my B field. If I go this way with it, right? There's less B field through that loop now. Or if I make these two what we call perpendicular to each other, now my area vector is this way, my B field is this way. This would be, if I use my cosine term, this would be zero flux. There's no B field entering through here. That was the idea behind what magnetic flux was. Flux is simply the measurement of how much the magnetic field or how much magnetic field is in a loop of wire. Electromagnetic induction is the phenomenon in which we see a changing magnetic field inside a loop, which induces an electromotive force, and in effect, it induces a current through that wire. Let's take some notes. Let's take an example of what I'm talking about here. So let's imagine this, right? Let's imagine I have a bar, just a conductive metal bar, and it is in a magnetic field that is pointed into the page. I've got a bar here, it's pointed in the page. That bar is neutral, it is not charged. There are positive and negative charges throughout the whole thing. I've got 1, 2, 3, 4, 5, 6, perfect. A totally neutral bar, right? As that bar moves through this magnetic field, just a bar moving through that magnetic field, there's a force applied on the charges in that bar. Let's use our right-hand rule to figure this out. As I move to the right, all these positive charges are my thumb using my right-hand rule. My thumb points to the right. It is in a second magnetic field that is into the page. What you'll notice is that means those positive charges, as this bar slides through the magnetic field, those positive charges experience a force up the page, which means after some amount of time, after moving through the magnetic field in this way, the force applied on those positive charges actually begins to polarize this bar. You see the positive charges are forced to the top. The negative charges are, by default, forced to the bottom, where I get this polarization. I get this potential difference to form in this bar. Now, because this bar is not connected to a loop, there is no current, there is no flow of charge, but there certainly is an induced potential difference, right? Now, imagine this. Imagine I go ahead and I take a wire now. I take some wire. Let's say it's like a free wire. There's like holes in both sides, but that wire runs through this bar, around, and then back to this bar this way. So the bar can actually slide along this conductive material. If this is true, and I have got a very high potential up here and a very low potential down here because of the difference in charge between top of this bar and bottom of this bar, what you can imagine is if I connect these, there will be a current that flows in this direction. That's the direction current will flow. It'll flow from the positive potential to the negative potential to keep this thing okay. And as it continues to move, we'll continue to see an increase or a force upward, and these positive charges will continue to flow. I will be inducing a current because of the flux, because of the change in magnetic field I'm experiencing here. Okay? So this is where we get this equation, right? We get the equation out that the electromotive force is equal to the magnetic field a object is in, it's experiencing, and it's multiplied by the length of the wire and the speed that the wire moves in. And then we go ahead and throw a negative sign out here because it's opposite. But basically what we're saying is that there's a potential difference created when a bar or a wire is moving through some magnetic field. And then again, we can go ahead and look at this like, what is this V? Why is there a V here? Well, this is the speed at which the charge is moving, And that charge is related to the magnetic field because current is the rate at which we see things moving. So this is all relative. There's a speed of the bar moving through a field. There's a field. And then how big is that wire to create that potential difference? Because we know if that length of wire is much, 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 much larger, the difference, the distance between these things will increase, and therefore the potential difference will also increase, VED, right? Like that's how that works, okay? So now, let's go ahead and take it one step further. If we understand how this difference is created through this, we can also now utilize what's known as Lenz's law. Lenz's law is a method for us to predict which direction the current will go in as an object moves through a magnetic field. Check it out. As this object moves from here through the magnetic field, through that field, as it does that, we would say, as it goes from here to say now the bar is over here, we would say that within this loop of wire, right, within this loop of wire, we have just increased, we have increased the magnetic field that is into the page. Inside that wire. We've increased the amount of B field pointed into the page inside that loop. Now, that disrupts the equilibrium that this system is experiencing. So in order for the system to remain in equilibrium, what's going to happen here is that Lenz's law states the current induced in this loop will oppose the change in magnetic field. So if I increase the B field into the page, the opposite of that, or the opposition to that, would be to increase the magnetic field out of the page. Okay, that's the opposition to the change that was just experienced by the loop of wire. Now, I can't just create, or the circuit just can't create a magnetic field. Instead, the current induced in that loop will produce an increase in B field into the page. So the third thing that's going to happen is, in order to do this, which direction will the current need to flow here in order to produce outward pointing magnetic field lines? So let's think. Using my second right-hand rule, here's the loop of wire. I need to see my fingers coming out of the page inside this loop. And if I do that, notice my thumb is moving in the counterclockwise direction. Well, folks, that's exactly the direction we predicted current would flow based on what we saw in terms of the way our right-hand rule works as the charge difference appears on this plate. So Lenz's law can be described using our right-hand rule and understanding that as charges move through this field, the force produces a potential difference. That potential difference, when it's connected, creates current. Or we can explain it by saying, hey, the changing magnetic field, or the changing flux, is increasing it, into the page. The opposition to that, which is Lenz's law, the opposition, we want to oppose that change, is an increase in B field out of the page. How can we get that? We can get that if the current is counterclockwise. This is Lenz's law. Basically, it's saying any change made will be opposed by the induced current. And folks, that kind of makes sense why there's a negative side or a negative sign out front of here. Now, let's recap. We have defined over the last two videos, we've defined what magnetic flux is. It's the amount of magnetic field through a loop of wire. And we can change that by either changing the amount of loop in that field or the relative angle that that loop has with the magnetic field. Next, we've talked about electromagnetic induction. And what that means is if there's a change in the magnetic field through that wire or a change in the flux, if there's a change in flux that induces a potential difference of charge. How do we explain that? We explain that using our right-hand rule. There's a moving bar, moving charges. There's a magnetic field. It applies a force on the charges in that bar, and that creates a potential difference. That potential difference has a special name in this case, and we call it the electromotive force. That potential difference has the ability to move charges when connected to a loop of wire. That loop of wire, when connected from the high to low potential, allows current or charge to flow through that loop. How can I predict the direction that that charge flows in? I can use what's called Lenz's law, and Lenz's law simply states that a change in flux will be opposed by the induced current. And that's exactly what we see here, right? If I increase the B field into the page, the opposition to that is the increase in the B field out of the page. How do I get an increase in B field out of the page? Through current. I would say the counterclockwise current will produce a magnetic field out of the page, and that opposes the change to hopefully restore the system to an equilibrium. These are the two major things I need you to take away from this video, or I guess the three major things to take away from this video. Recap flux, introduction to electromagnetic induction, and Lenz's law. If you got questions, drop it in the comments, send me an email, or ask me in class. Until next time, see ya.